Welcome, Hornets. In this video, we are taking a look at the sketching of curves of complex rational functions. I'm not trying to make them overly complicated, but we are now at the point where there's quite a bit going on here. So, once again, as we have been doing each and every single time, we look at what we start off with and we try to find our basic parts. For example, we can clearly see with the power greater in the denominator has a horizontal asymptote, and that horizontal asymptote is y equals 0. It also has a vertical asymptote, and that vertical asymptote is x equals 0. If we factor the 6 in the numerator and break it down into x plus 1, x minus 1, we can see that we have two zeros. These zeros are located at -1 and 1. And there are no y-intercepts. Notice that if we try to make the y-intercept with x equaling 0, we end up with -6 over 0. That's our asymptote. So we have no y-intercepts. So we have our horizontal asymptote, our vertical asymptote, we have our zeros, we have our y-intercepts. But one of the things that we weren't able to do before is determine our relative extrema and our points of inflection. This is what we are now going to be able to do with our first and second derivatives. Let's go ahead and start with the first derivative. I'm going to be using the quotient rule. Low d high, less high d low, square the bottom, and away I go. I end up getting a 12x times x cubed, and I'm subtracting the 6x squared minus 6 times a 3x squared, and this is all over x cubed, the quantity squared. Now, when we simplify this, we do end up getting -6 times x squared minus 3, and this is all over x to the 4th. And this can then factor into -6, x plus root 3, and x minus root 3. This is still all over x to the 4th. Our second derivative we can now work with. And we're going to work with this piece right here for our second derivative. And I end up with a -6 times 2x times x to the 4th minus -6 times x squared minus 3 times 4x cubed. This is over x to the 8th. And when I simplify this, I end up getting a very straightforward 12 times x squared minus 6 all over x to the 5th. Now, we can factor this, and when this gets factored, we have our 12 x plus root 6, x minus root 6 over x to the 5th. So be aware, these are the two first pieces we're going to be working with. We're going to make our two sine charts. I'm going to have my -6. I have x plus root 3, x minus root 3, and I actually have 4 x's from the denominator, or 1 over x's. Now, because they're an even number, we don't actually have to worry about them. They all cancel each other out, but it is still nice to see them. So we have our 0, root 3, and negative root 3. Remember, critical values are where we have asymptotes and our derivative equal to 0. So we have negative, 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 negative. We have a positive, a positive, a positive, and a negative. and a positive, negative, negative, negative. Now, all of these are positives and negatives, and they'll all cancel. So we end up with a negative, positive, negative, positive. Notice this tells me that f of x is increasing, and this is on the two intervals from negative root 3 to 0, which is an asymptote, and then from root 3 to positive infinity. F of x is decreasing on our mutually exclusive intervals, negative infinity to the negative root 3, obviously, except that shared point. So that's not valid. It's not mutually exclusive. And there we go. We're now going to have to do our sine chart for this group. And once again, we now have 12, x plus root 6, x minus root 6. The problem is we now have to do at least one of the 1 over x's. Okay? The other 4 will all cancel each other out. I'm going to go ahead and I'm going to put in my 0 right smack dab in the middle. We have our root 6. We have our negative root 6. Once again, just setting up my sine chart. 12 is always positive. We have a positive, 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 negative, positive, negative, 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 positive, positive, negative, negative. And then keep in mind that you have 4 of them, and those 4 are all just going to cancel each other out. So we end up with a positive, a negative, a positive, and a negative. This tells me that f is concave down on the two intervals, negative infinity to negative root 6, and then from 0 to root 6, and f of x is concave up on the other interval, negative root 6 to 0, and then root 6 to infinity. Now, I recognize that I have points of inflection. There's a point of inflection here. There's a point of inflection here. I have a relative maximum, relative minimum here. And I have a relative maximum here. Please remember that this is an asymptote at x equals 3. And so we're not going to have anything there. So I've got negative root 6, negative root 3. The asymptote is right here at 0. We have root 3 and root 6. When we plug them in, we get negative 2.041. That makes this the mirrored image, 2.041. And this is 2.309. Therefore, negative 2.309. And now we're ready to start graphing this. So I have my asymptotes. And unfortunately, it's hard to see them. So I'm going to kind of make it clear it's the asymptote, x equals 0. I have the horizontal asymptote. And that's y equals 0. So we're now going to start putting some of this information in. For example, I have my negative root 6, negative 2.041 4, this is a point of inflection. Has a mirrored image on the other side. I have a relative maximum over on this side. And I have a relative minimum on this side. Now keep in mind, I still have zeros. I have a 0 here at -1, and I have a 0 here at +1. And now when I draw my graph, I have my concave up from -√6, going up towards the 0. This side we have concave down. And then I have concave up. It heads toward infinity and heads toward infinity. Now I want to plot these points. All of these points that we found on our graph. This one is 1, 0. We have √3, 2.309, √6, 2.041. Don't forget y equaling 0 here. This is -√3, -2.309. And this is -√6, -2.041. And all I've done is started plotting everything, putting it onto the graph, and trying my best to draw it. So let's review it. I started off with the two asymptotes. I plotted the 2 points of inflection, the 2 maximas, minimas, and the 2 zeros. I then did the concave up portion of the graph and the concave down portion of the graph, then concave down and concave up. I then went back and plotted my x-intercepts, my points of interest. And that is our goal, trying to be able to graph and sketch a graph based upon information we know. A couple of things to take note. Notice that the order of this, so we have the degree on top and we have the order on the bottom. Notice that our order is odd. And some people aren't aware of this, but when the order is odd, the curve has to approach in opposite directions of infinity. So if I had an even order, they'd both be going in the same direction. In an odd order, they go in opposite. And I've mentioned this in the past, but here's a perfect example of where it comes into play. All right, so here we have an example of a complex rational function. Hopefully you will go back over this video as many times as you need in order to be able to graph them. Otherwise, ladies and gentlemen, gentle folks, hornets, students, guys, gals, and pals, please be well, be safe, take care, and thank you for watching. Good night. Good night.